The database we used is extracted from Kaggle and was put into Google BigQuery for analysis and machine learning. The variables are the following. There are 5 of them. The input confirmed, which are the number of confirmed cases. Recovered, the number of recovered COVID-19 cases. Country region is where it was detected, the case. And the date is a date of observation. And as an input variable, we have death, which is the impactful target for analysis. And it predicts deaths based on country, date, and recovered. It is a supervised problem, which means we have input and output pairs. We're working with labeled data, which is the death column, as I said earlier. And the model learns from historical data where the input-output relationship is known. It is obviously a regression problem since the target variable, which is our death column, is continuous and numeric.
Now I'm going to talk about the analysis of the variables. We first did some histograms and we find the maximum value of each variable. We later on did the variable cleaning, in which we checked for null variables. And we deleted latitude, longitude, whole region, and province state, as they were not significant for the analysis. We further on transformed the variables into logarithms to reduce the impact of endurance of outliers. We used group by to create a new column for analyzing active cases. We grouped by country region to calculate the sum for confirmed cases, recovered cases, death, and active cases. As we can see, USA has the highest number of active cases and China dropped in active cases, suggesting a high recovery or fatality rates. We also use join to merge the data frame clean with the population data based on the country region. We use left join for this. We don't have like the corresponding population of the data, so we fill that the columns with a default of 1 million. We use also Google APIs for the weather, as while doing the research we found that understanding the weather conditions in different parts of the world, including the countries, we can identify environmental factors that can contribute to the spread of COVID-19. The temperatures we retrieved were from United States, India, Brazil, Canada, Russia, and United Kingdom. The correlation analysis, we find that confirmed deaths have a high positive correlation, as regions with high confirmed cases have a high rate of death. And we also found that active cases and deaths have negative or close to zero correlation. This indicates that it may be that current cases do not directly correlate with total cumulative death. We did random forest, in which we measure how much each feature contributes to reducing the error in predictions. We found out that death occur at a smaller scale compared to confirmed and recovered cases, as we can see in the bar chart. We split the data into training and testing. We found that the training is 80% and testing is 20% of the data set.
In the scatter plot diagram, we can see a regression model we did by using SQL. This regression model visualizes the relation between features, which are confirmed and recovered, and the confirmed cases are higher than recovered cases. We can also see the metrics given by this linear regression model, which mean absolute error is 563, squared error 5,822,000, and so on. The same with the XGBoost regression model, with predicting deaths based on confirmed and recovered cases. Most predictions clustered at lower ranges with some outliers, which might be indicating of anomalies or extreme cases. Here we can see the metrics given by the XGBoost regression model.
We created models with auto machine learning. The top performing models were linear regression, ridge regression, and lasso regression with a perfect R-squared and an RMSE and MA of 0.0. And the best model is linear regression, as it has perfect scores overall and it fits perfectly with the dataset. Well, when comparing models, we found out that the linear regression, ridge regression, and random forest dominate near perfect R-squared scores. However, linear regression is the best model in this case, but the perfect results might suggest overfitting. And the models that can be discarded are lasso regression and support vector regression. In conclusion, the ridge and random forest demonstrate strong potential for accuracy for predicting COVID-19 deaths. The preferred model in this case would be rich regression and random forest, as it's the most balanced choices. And it is important that we should validate linear regression. As I mentioned before, it can lead to an overfitting, and that is why it has overall perfect scores. Thank you.